The James Webb Space Telescope recently gave researchers a major shock with its most recent pictures. There's a world out there that has been around for billions of years. It's a space-time narrator, witnessing stars being conceived and saying farewell. However, the intriguing thing is that this old system holds secrets we never even dreamed of. So, what kind of stories might it tell us about the universe? What has it experienced all this time? Prepare for a journey into space with the James Webb Telescope, where we'll explore the mysteries of this ancient world. A mysterious interloper is on a path to collide with Stephan's quintet, potentially foreshadowing a major cosmic conflict. We know that there is a group of 5 galaxies, each with its own unique identity: NGC 7317, NGC 7318A, NGC 7318b, NGC 7319, and NGC 7320, located around 270 million light-years away in the constellation Pegasus. This galaxy group, known as Stephan's Quintet, was recently examined at the 241st meeting of the American Astronomical Society. Researchers used the powerful tools of the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope to peer into the heart of Stephan's Quintet. What they discovered was nothing short of stunning: an ensemble of shock waves, disturbances, and the formation of new galaxies. Yet here comes an interloper galaxy, NGC 7318b, hurtling into the group at a breathtaking speed of around 800 kilometers per second. To put this into perspective, a journey from Earth to the Moon at this speed would take only 8 minutes. The collision sets off a massive shock wave, resembling a sonic boom several times the size of our own Milky Way. Here's where it gets fascinating. This violent impact isn't triggering an explosion of star formation within the galaxies themselves, as one might expect. Instead, the action unfolds in the intergalactic medium, where there is almost no star formation to obscure our view. It's like having a clear window into the event. The shock wave encounters an ancient cloud of gas, likely formed from a previous interaction between 2 galaxies in the group. This impact initiates a series of events that have left astronomers astonished. The shock wave creates an extremely turbulent cooling layer, leading to the recycling of warm and cold molecular hydrogen gas. Why is this important? Because molecular hydrogen is the raw material that could eventually give birth to stars. Understanding its fate unlocks the secrets of galaxy evolution. Let's zoom in on the remarkable observations made possible by ALMA's Band 6 receiver, developed by the U.S. National Science Foundation's National Radio Astronomy Observatory. This instrument allowed researchers to examine 3 key regions in unprecedented detail. For the first time, a clear picture emerged of how hydrogen gas is moving and shaping itself in response to the cosmic turbulence at the core of the main shock wave, known as Field 6. A massive cloud of cold molecules is breaking apart and unfurling into a long tail of warm molecular hydrogen. Interestingly, the gas does not survive the shock but undergoes cycles of heating and cooling. The tail extends beyond the time it takes for the clouds to be destroyed, indicating a remarkable process of intergalactic recycling. Yet that's not the only surprise. In Field 5, researchers observed 2 cold gas clouds connected by a stream of warm molecular hydrogen gas. One of the clouds, resembling a high-speed bullet of cold hydrogen, pierced through a large, filament-like strand of diffused gas, creating a ring in the structure. The collision energy feeds the warm envelope of gas around the region, though the detailed implications of this phenomenon are still being unraveled. Now, let's venture into Field 4, the most tranquil area among the observed regions. Here, researchers found a steadier and less turbulent environment, allowing hydrogen gas to collapse into a sphere of stars. What's truly remarkable is the belief that a small dwarf galaxy is currently forming. The shock wave here has disrupted previously massive clouds of dense gas, leading to the formation of new stars, a typical outcome in the violent dance of galaxies. Back in 2010, observations with NASA's Spitzer Space Telescope hinted at massive clouds of warm molecular hydrogen mixed with extremely hot gas. However, these clouds should have been destroyed by the massive shock wave sweeping through the group, raising the question of how they survived. To unlock this mystery, researchers required more technological firepower. ALMA's capabilities, combined with the James Webb Space Telescope's imaging power, provided a more comprehensive understanding of the interplay between cold, warm, molecular, and ionized hydrogen gases in the wake of the giant shock wave. But as we bask in the beauty of these discoveries, we must recognize the gaps in our understanding. Spectroscopic data is key to unraveling the remaining mysteries. We need to know the movements of the gas, the velocity of the warm gas, its temperature, and how it responds to the shock waves. Essentially, we've heard one side of the story, and now it's time to discover the other. Yet, how do such violent cosmic events shape the fate of galaxies? What role does turbulence play in the grand cosmic ballet, and what can the intergalactic medium reveal about the primary processes governing the universe? The National Radio Astronomy Observatory and the Atacama Large Millimeter/Submillimeter Array have opened a window into the cosmos, revealing a massive recycling plant where giant molecular clouds crumble and new galaxies are born, all triggered by the shock waves of celestial collisions. These findings not only expand our understanding of Stephan's quintet but also raise new questions about the universe that surrounds us. Recently, the James Webb Space Telescope provided us with an enthralling glimpse into this cosmic birthing process through a mesmerizing image of an object named HH22. I can't help but wonder, what secrets does this distant corner of the universe hold? How does the birth of stars, like our Sun, shape the universe? HH212, nestled in the Orion constellation, offers a snapshot of a star in its infancy, a mere 50,000 years old. The image captured by Webb reveals a stunning display of pink-red jets shooting out in opposite directions. These jets unveil the invisible drama unfolding within a dense rotating disk of gas and dust. But why can't we see the protostar itself? What cosmic forces are at play in the creation of these brilliant jets? To understand the dynamics at play, we turn to insights from Professor Mark McCaffrian, a senior science advisor at the European Space Agency. He explains that the outflows of gas, depicted in the image as pink-red, are the star's way of managing its birth. But how exactly does this work? Professor McCaffrian unravels the mystery, detailing that as the central lump of gas contracts and spins, the challenge lies in keeping it from spinning too fast and tearing apart. The solution? Jets and outflows. These bipolar structures, driven by magnetic fields, eject material through the poles, creating the mesmerizing jets we see. I'm struck by the significance of the pink-red color in the image. It represents the energetic processes shaping this young star. The presence of atomic hydrogen particles, with two hydrogen molecules bonded together, is observed. Shock waves flowing through surges stimulate them, making them glow brilliantly at the infrared frequency of 2.12 microns. It's interesting to think that the variations in this astronomical work of art are for show, as well as hold significant information about the components involved in star formation. The image of HH22 reveals the intricacy of the star's surroundings. The dense, infalling disk of gas and dust cloaks the protostar, adding an air of mystery to the cosmic scene. When we look closely at the left and right planes in the annotated image, we can trace clusters of brightness and count the bow shocks. Faster material crashes into slower material just a little ahead, creating symmetrical structures that captivate the eye, except for a muddled bow shock on the right. Yet, what causes these deviations, and what stories do they tell about star development? Astronomers have been observing HH22 for a long time, recording its evolution through periodic images. Webb's new view, multiple times sharper than its predecessors, opens a window into the complex processes driving star formation. Repeat observations even enable the measurement of the speed at which these components are moving, remarkably, at speeds exceeding 100 kilometers per second. While I once believed that HH represented atomic hydrogen, it actually pays tribute to astronomers George Herbig and Guillermo Haro. These pioneers led groundbreaking work on objects like HH212 in the 1940s and 1950s. It's astonishing how their legacy lives on through Webb's capabilities, which not only capture incredibly sharp images but also expand the range of colors it can detect. As Professor Maction highlights, the main wavelength for observing objects like HH212 is 2.12 microns, significantly longer than the mid-visible range. The ability to see at various wavelengths, previously unreachable from ground telescopes, has produced a vivid color image of HH212. This newfound ability allows scientists to gain deeper insights into the processes at play. The profound impact of Webb extends beyond HH212 to its younger cousin, HH21, located in the Perseus constellation. HH21, much younger and estimated to be only thousands of years old, offers a fascinating parallel to the early stages of our Sun. Considering this, I'm struck by the cyclical nature of cosmic evolution. How do these objects in the Perseus constellation compare to HH212, and what unique lessons do they hold about star formation? Recent advancements in astronomy have allowed scientists to glimpse shock waves rippling through the universe for the first time. Imagine our universe as a giant Swiss cheese, where galaxies are not evenly spread but clustered together in massive groups connected by delicate filaments of gas and dark matter. These filaments make up the cosmic web and serve as the highways along which galaxies travel, pulled by the gravitational forces governing the universe. The spaces between these structures are not empty voids but rather fascinatingly interconnected areas. Here's the exciting part. Scientists have long theorized that when galaxy clusters merge and filaments collide, shock waves are generated, triggering a chain reaction of cosmic proportions. Previously only predicted by simulations, these shock waves have finally been observed by astronomers. The challenge for scientists has been identifying these shock waves, particularly in the filaments, which are much harder to spot than galaxies. It's like trying to find a needle in a haystack, or, in this case, trying to detect shock waves in the vastness of the cosmic web. However, a team of scientists, led by radio astronomer Tessa Wernström, found an ingenious way to overcome this challenge. Instead of searching for individual shock waves, they combined over 600,000 pairs of galaxy clusters connected by filaments, creating a stacked image that amplified the faint signals produced by the shock waves. Isn't it fascinating to think about the technology and innovation that allow us to see beyond what our eyes can detect? Imagine the excitement of the scientists as they sifted through the noise and uncovered hidden signals. The resulting image revealed a faint, highly polarized radio glow from the filaments. Now, you may wonder, what does it mean for radio waves to be highly polarized? In the universe, highly polarized light is unusual, but it is precisely what scientists expected from shock waves. This arrangement of radio waves provides strong evidence of shock waves in the cosmic web. It's like having a cosmic compass pointing us towards these invisible yet powerful phenomena. Let's delve a bit deeper into the significance of this discovery. The polarized radio emissions not only confirm the presence of shock waves but also offer a unique opportunity to study the magnetic fields surrounding the cosmic web. These shock waves act like messengers, not only revealing their presence but also conveying information about the magnetic fields shaping the universe's filaments. Astrophysicist Marcus Bruggen emphasizes that these shocks play a critical role in demonstrating the existence of large-scale magnetic fields enveloping the filaments. Radio astronomer Tessa Wernström highlights this mystery, pointing out that magnetism is a fundamental force of nature, yet our understanding of its role in shaping the cosmic web is far from complete. Isn't it fascinating to ponder the fundamental forces that govern the universe, forces that are essential to the very fabric of space yet remain mysterious in their origin and significance? The discovery of shock waves in the filaments of the cosmic web not only confirms theoretical predictions but also invites us to consider the broader implications. How do these shock waves influence the evolution of the cosmic web over time? What role do magnetic fields play in shaping the cosmic structures we observe? And, most intriguingly, what new revelations await as we continue to explore the universe? What grandiose mysteries do these shock waves convey inside their unpretentious radio transmissions? One invigorating part of this disclosure is the indirect glimpse it offers into the magnetic fields that envelop the cosmic web. It's like solving a puzzle where each piece reveals a bit more of the complex picture. We must also recognize the remarkable strides made by astronomers and scientists in uncovering its secrets. The blend of advanced technology, meticulous observation, and innovative data analysis has allowed us to pierce through the cosmic veil and glimpse the invisible forces at play. Scientists, despite their impressive discovery of shock waves, still find themselves on the brink of understanding these fundamental questions. Imagine if, in the coming years, we unlocked more secrets hidden within the cosmic web. What if we gained a deeper understanding of the cosmic forces that have shaped the universe since its inception? The discovery of shock waves in the filaments of the cosmic web opens a new chapter in our exploration of the universe. It's a testament to human curiosity, innovation, and the relentless pursuit of knowledge. The cosmic web, once a mysterious backdrop to the dance of galaxies, now reveals itself as a dynamic and interconnected tapestry shaped by the invisible forces of shock waves and magnetic fields. Look closely, what do you see? It appears like a hazy, pixelated red and green smear dispersing into space. Yet this unassuming visual is the featured galaxy, Aztec 71, captured by the powerful James Webb Space Telescope. It's not some ordinary, easily recognizable galaxy with a distinct name and captivating features. This cosmic resident is just a string of numbers and letters, residing at a distance so vast that it evades the focal lenses of many telescopes. However, thanks to the James Webb Space Telescope, we are granted a glimpse into Aztec 71 as it existed an astonishing 900 million years after the Big Bang. The image we have of Aztec 71 is far from the stunning portrayals of galaxies and galaxy clusters we often encounter. Instead, it appears as a faint speck of light. Yet this seemingly unremarkable view holds profound significance for our understanding of the early universe. Jed McKinney, a study author from the University of Texas at Austin, expressed his excitement about this discovery, saying, "The fact that even something that extreme is barely visible in the most sensitive imaging from our newest telescope is so exciting to me. It raises the possibility that there might be an entire population of galaxies that has been hiding from our gaze." The early universe, as depicted by Aztec 71, could have been much dustier than we previously imagined. This discovery has the potential to shed more light on the evolution of the universe since the explosive birth of the cosmos approximately 13.8 billion years ago. The faint, mysterious glow of Aztec 71 is a reminder of the hidden complexities that astronomers are only beginning to unravel. But how did Aztec 71 come into the spotlight? It was initially detected as a massive source of light by the James Clerk Maxwell Telescope in Hawaii. Subsequently, the ALMA radio telescope in Chile captured an impression of this cosmic enigma. However, it seemed to vanish when viewed by the Hubble Space Telescope, leaving experts baffled. McKinney exclaims, "This thing is a real monster." Despite its modest appearance, Aztec 71 is a stellar powerhouse, forming many new stars each year. It's a reminder that appearances can indeed be deceiving in the vast expanse of the universe. As part of a global effort to map the earliest structures of the universe, McKinney and his colleagues embarked on a mission to locate Aztec 71 using data collected by the James Webb Space Telescope. This revolutionary observatory boasts an exceptional infrared eye capable of seeing through the dense dust storms prevalent in the early universe. Before Webb came onto the scene, galaxies like Aztec 71 were nearly impossible to detect. The light emitted by ancient stars inside these dust-laden galaxies was absorbed at optical frequencies by the dust itself. However, this absorbed light was then re-emitted at faint, longer wavelengths that Webb could uniquely capture. This remarkable capability revealed a collection of galaxies that had previously eluded the Hubble Space Telescope, aptly named Hubble Dark Galaxies. The implications of this discovery are profound. McKinney highlights that our understanding of the history of galaxy formation is biased because we're primarily seeing the unobscured, less dusty galaxies. But what's next on the horizon for McKinney and his team? Their plans involve uncovering more faint, hidden galaxies using the wealth of data provided by the James Webb Space Telescope. This striking instrument not only allows us to look back into the farthest reaches of the universe but also has the extraordinary ability to penetrate the thickest of dusty veils. The James Webb Space Telescope has opened a new chapter in our exploration of the universe, challenging preconceived biases and enticing us to peer into the hidden corners of space. What other celestial secrets await our discovery, concealed behind the cosmic veil of dust and time? It's a thrilling journey of cosmic exploration that keeps us yearning for more answers to the fundamental questions about our existence in this vast, mysterious universe. Did you catch all those astonishing revelations? The universe is like a giant puzzle, and we're uncovering its secrets piece by piece. But guess what? The excitement doesn't stop here. Join us on our journey and never miss out on the next big cosmic discovery. Hit the subscribe button and turn on notifications. A big thank you for joining us on this space adventure. Until next time, keep looking up, stay curious, and keep dreaming among the stars.